let's see here.
We just passed the postulate 2, right?
We are just getting into, we're basically on page 369. Yeah. All right, so I will begin with a word of prayer. So, dear Father, we thank you for this day. Thank you for these students. Just ask you to guide our steps today. Help us to understand a little bit more about your creation and about how to understand quantum mechanics in terms of careful mathematics, Lord. In my prayer, Jesus, amen. All right, so I'm going to start out with a calculation, actually. So he says if you've got the position observable x hat, right, and the momentum observable p hat, all right, and then he says it's equal to minus I h bar, right, partial x. Now this h bar is equal to what? H bar is equal to Planck's constant h divided by 2 pi. This is, standard physics notation. And he doesn't really explain, right, why momentum should be that, and yet that's what it is, right? In some sense, that is kind of natural from the perspective of a Fourier analysis, right? So there's something to be seen there. There's an interplay between the Fourier discussion and quantum mechanics, right? Like, just saying, because we've seen this pattern before, right? Like, multiplication and p became, it's kind of like that, but okay, anyway. So the interesting thing, of course, is to calculate the commutator of x hat and the momentum acting on, let's say, a wave function. And so by definition, that is x hat p hat psi minus p hat x hat psi. And if you look at, chapter 7 here in, where are we? It's important that I say this in various videos because otherwise people lose track. I'll lose track after about 10 years what book I was in, Third edition of Introduction to Hilbert Spaces with applications by Loknev, Debnev, and Pyotr Mikuzinski. Anyway, we're in chapter 7, which is, of course, on quantum mechanics. And I think if you look at his observables, they pretty much fall into 2 categories. They're either multiplicative operators or they're derivative operators. That's pretty much, we have all this great wealth of diversity of examples earlier in the book about different kinds of operators. There's integral operators, there's shift operators, there's all kinds of wacky stuff, right? But once you get into the quantum mechanics chapters, there's either multiplicative operators or there's derivative operators, and there's linear combinations thereof. Like, that's pretty much it. Although the direct delta does appear in a bit. Anyway, so this is the commutator, and of course you have to sort through what that means, right? So like that's x hat minus I h bar partial psi partial x minus I h bar partial x of, and x hat on psi, it just gives you psi x, right? I mean, that's the multiply by x operator is kind of boring. There it is, right? And of course this also is kind of boring. It gives you minus I h bar x partial psi partial x and minus I h bar psi minus I h bar x partial psi partial x. Of course, let's see here, what went on? I feel like I messed something up here. What did I mess up? Can you tell me? I feel like every class is a party today. This is like the next to last day of classes here, Audric, and like all of the classes are just like people yelling, hollering, and hooting. It's so annoying. Yeah,
After that comment should be great.
it's h divided by 2 pi. Yeah. In fact, generically speaking, if I was to talk about Audric slash, it would be u divided by 2 pi. It's a generic notation in physics.
Okay.
Slash is division by 2 pi.
So why don't we call it tau bar?
That's a good, I don't know. Tau bar. That is a very obscure reference, and I appreciate it, Audric.
Sorry.
That's horrible. So the thing is that this is plus because, why? Because there's a minus from the commutator and there's a minus from the definition of p hat. And I need to put those two together to give me pluses, which is good because then, and that cancel. And it just leaves you with, I h bar psi, right? And since this holds for all psi, this tells us that we have this fundamental commutation relation, x hat with p hat is equal to I h bar, right? In other words, the position and the momentum operator do not commute. All right. Now, another calculation we should do is with kinetic energy. So as example 1. So position and momentum do not commute. Example 2, if we talk about kinetic energy, T in terms of momentum, that's, p hat squared divided by 2m, right? And then you can calculate the commutator, t hat, I guess I should say, and you can work out that the commutator of t hat and p hat is, well, 0. And you could do this in one dimension. We could do it in more dimensions, right? Like, this could be just as well as 3-dimensional. We could be talking about 1 over 2m px hat squared plus py hat squared plus pz hat squared. So the total 3-dimensional kinetic energy operator, and that, if we did t hat with any one of those guys, we'd get 0. So the kinetic energy commutes with momentum, right? However, and so that would mean the Hamiltonian would commute with the momentum operator. So let me write that down here. So free particle. What's a free particle? Yeah, so it's like the oh man, I still haven't. I was going to read up on the rigged Hilbert space. I haven't yet. That's going to have to wait till next class, unfortunately. Curses. Anyway, that's what I was going to do. Dang it. Oh well. So if your potential is 0, then it's a free particle, right? So in other words, for a free particle, the potential energy is 0, and so basically the Hamiltonian operator is equal to the kinetic energy operator for a free particle. And so what example 2 could be restated to say is that for a free particle, the momentum, so of course the eigenvalues of the Hamiltonian are called the energy, right? The energy eigenvalues, and this would mean that the Hamiltonian commutes with momentum. So you could, as we'll understand as we go on, simultaneously, you could have eigenstates that are simultaneously energy eigenstates and momentum eigenstates for a free particle. However, this is not the case anymore if we have, if the particle is not free, right? So for example, example 3, if we have, the Hamiltonian operator is equal to the potential, the kinetic energy operator plus the potential operator, right? Where here we're just, basically, this is a very silly operator. V hat acting on psi is just going to give you like psi of x. Excuse me, my bad. The potential energy times psi of x. I mean, that's That's what we mean by V hat. It's a multiplicative, it multiplies by the potential energy function, whatever that happens to be for the system. And so the thing is, if we look at the commutator of momentum, all right, with the Hamiltonian in this case, we get the commutator of the momentum with the kinetic energy plus the potential energy, right? And in order to understand the bracket, we have to let it operate on a test, a test function psi, or in this case, you could think about it as a wave function, as we'll be describing in this chapter. That's just a meaningless word at the moment in some sense. But coming up is the statistical interpretation. That's like, okay, anyway, going on here. So, as I just discussed, and we'll do this one-dimensionally, but the story remains the same for 2 or 3 dimensions, all right? So, of course, momentum commutes with the kinetic energy, but on the other hand, momentum does not have to commute. In fact, probably doesn't commute with the potential energy, because what that is, right? So this piece goes to 0, a la example 2, and this piece, on the other hand, is minus I h bar partial x of what? Of v, which is a function of x times psi of x, all right, plus, I'll pull the I h bar out, but v, which is a function of x times partial psi partial x. So we have a product rule, right? You have a product rule that happens here, and not everything goes away. So you end up with, minus I h bar partial v partial x times psi. Because the other term in the product rule cancels with the other term from the commutator, and it just leaves you with this term derivative in the potential energy. So in other words, what we have here is the fact that the commutator of momentum and the Hamiltonian, in the case of a system with potential energy V, is just equal to minus I h bar partial v partial x, all right? And there's no reason that that has to be 0. Although, if your potential energy was constant, that would be harmless enough, right? But if your potential energy is constant, you might as well make it 0 anyway by the rules of, by the way things work, right? I don't know. Okay, so I just want to do these calculations because I think they're nice to see. They're not particularly complicated, and they should help center this lecture. All right, so this implies the momentum and energy of a particle moving in a potential field cannot be determined precisely and simultaneously. All right, again, as we were talking about last time, we need the commutator of the 2 observables to be 0 to simultaneously diagonalize them with the same eigenstate. All right, so the third consequence of postulate 2, he says, is that the eigenvectors belonging to different eigenvalues of an observable operator form a complete orthonormal set. So this is the, this is the message delivered by Griffith's quantum mechanics, ad nauseum. I think every basic quantum mechanics course basically makes like a huge point of this, that you can pick whichever particular physical system you like one-dimensionally with the same kind of bounds as the problem you're looking at, and you can expand an arbitrary wave function in terms of the basis of the eigenstates of, like you.
Yeah, you're right. Dr. Johnson was trying to nerd out about this.
Oh yes, they get very excited about this because it's weird that you're solving a problem. You're solving a problem. You're solving one physical problem with the basis of eigenstates from a different one, and that's a really weird thing from a physics perspective, right? But it's just the complete orthonormal system at play is what it is. So anyway, So just to put some notation up on the board here, the complete orthonormal system looks like this. Psi n, psi m equals to integral minus infinity to infinity psi n of x conjugate psi m of x dx. And that is, of course, going to give you the Kronecker delta mn and m. Don't we have dorms? Can't people go and like hoot and holler in the dorms? Isn't that like, I don't know, like, Audric, I'm stuck in between a land of two like ridiculous extremes. Like, you go to UWA and it's like there's nobody there. It's just a ghost town, right? There's nobody, you know? And then here, I'm tripping over people everywhere. There's got to be some kind of middle ground, you know?
I went to a university with 20,000 more students in Liberty.
Ooh. Yeah. Yeah, I guess. You can come here for some solitude, I guess. I will say that the pastor I like a lot on YouTube, his church is actually close to Austin. So, okay, anyway, where was I? So we can expand any wave function. I shouldn't say wave function. This is not a wave function. Excuse me. This is a state vector. I need to be careful because there is a distinction between the term state vector and wave function. Wave function is time dependence. This does not have time dependence. All right, so this set of eigenvectors forms an orthonormal basis in the associated Hilbert space, and this set is often called the eigenbasis for the observable operator a hat. All right, so there's no a hat going on here, but of course the assumption is that if we have a hat and we act on psi n, right, we get lambda n psi n, right? Like that. All right. Now forgive me, I'm going to have to pause right here. I have